Hi everyone, myself Aishwarya GS from Maharajah Institute of Technology, Mysore. Today in this session, I am going to explain about application analysis versus domain analysis. Firstly, we are going to learn about what you mean by analysis. Before going to application analysis and domain analysis, we are going to learn about what you mean by analysis. Firstly, analysis begins with the problem statement generated during system conception. The main agenda of analysis is to specify what are all the needs to be done and how it is done for a specific problem. And analysis makes it more precise and exposes more consistency of the problem statement. It has mainly three aspects of the objects. First one is static structure of objects, also known as class model. Next one is interaction among objects. It is also called as interaction model. And last one is life cycle history of objects, also known as state models. All these class models derived from real world entities and has divided into two stages. This diagram represents the overview of the analysis. When a problem statement is given, we have to generate request from the users, developers, or managers, and we are according to that request we are going to design a problem statement. uh, um, and with the problem statement we are going to build the models, mainly domain knowledge, related systems, user interviews, and lastly, according to that model we are going to segregate that as class model, state model, and interaction model. This picture also represents that how the domain analysis and application analysis works. The first one is domain analysis that mainly focuses on understanding the real world entities of a problem. The second one is application analysis. It is built on the basis of domain model, incorporating major applications artifacts that are seen by users and must be approved by them. First one is domain class model. The first step in analyzing the requirements is to construct a domain model. The domain model shows the static structure of the real world system and organizes into pieces. The domain model describes the real world classes and their relationships to each other. Information for the domain model comes from the problem statement, artifacts from the related systems, expert knowledge of the application domain, and general knowledge of the real world. We must consider the following steps to construct a domain class model. First one is finding classes. Prepare a data dictionary, find association, find attributes of objects and links, organize and simplify classes using inheritance, verify that access paths exist for likely queries, iterate and refine the model, reconsider the level of abstraction, group classes into packages. First one is finding the classes. The first step of constructing a class model is to find relevant classes for objects to the appropriate class domain. This includes physical entities such as person, machine, houses, as well as concepts such as seating arrangements, payment schedules, etc. All classes must make sense in the application domain, and not all classes are explicit in the problem statement. Some are implicit in the application domain or general knowledge. For example, in a system, their main intention is to sell tickets to performance at various theaters. Tentative classes would be reservation system, tickets, performance, and theater. Um, the main idea is to capture the concepts that are nouns are concepts, and concepts also expressed in other parts of speech that are such as reservation system and performance of the selling of the tickets in the theaters. Next one, after finding the classes of a specific problem, uh, to prepare a data dictionary, that is, isolated words have too many interpretations, so prepare a data dictionary for all modeling elements. with a paragraph precisely describes each classes and the scope of the class within the current problem, including any assumptions or restrictions uh, that may cause a problem statement. The data dictionary also describes association attributes, operations, and enumeration values. Next one is finding associations. Finding association between classes. It is mainly a structural relationship between two or more classes in an association. A reference from one class to another class is an association. For example, class called person should not have an attribute employer. Relate class person and class company with association works for. Association show relationships between classes at same level of abstraction as the classes themselves, while object valuated attributes hide dependencies and their nature. Next one is finding attributes. Finding attributes are the data properties of individual objects such as weight, color, height, etc. Attribute values should not be objects, and it uses an association to show and relate between two objects. Attributes usually correspond to nouns by possessive phrases such as color of the car and position of the car, etc. Unlike classes and associations, attributes are less likely to be fully described in the problem statement, and we must draw on our knowledge, the application domain on the basis of real world entity, and we must also find attributes in the artifacts of the related systems. Keeping the right attributes mainly plays a major role, um, like pointing out the objects, qualifiers, names, identifiers, association towards attributes, etc. Next one is to organize and simplify classes using inheritance. This is to classify using inheritance and share common structure to the problem statement. Inheritance can be added in two directions: by generalizing common aspects of existing classes into a superclass, or by specializing existing classes into multiple subclasses. That is also known as bottom up approach and top down approach. Next one is to verify that access paths exist for likely queries. This represent to see if they are sensible, if they are giving the sensible results where a unique value is expected. Is there a path or a unique result for multiplicity or many? This represents many, where the way is to pick out unique values when needed. It can be acceptable to have classes that are disconnected from other classes. This usually occurs when the relationship between a disconnected class and the remainder of the model is diffuse. Next one is to iterate and refine the model. A class model is rarely correct after a single pass. The entire software development process is one of continual iterations. Different parts of a model are often at different stages of completion. The main thing we find a deficiency in the initial stage of the model. We have to go back to the earlier stage and correct it. There are several signs of missing classes, like asymmetries in association and generalization, difficulty in generalization, etc. Next one is reconsider or shifting the level of abstraction. So far in analysis, we have taken the problem statement literally. We have regarded nouns and verbs in the problem description as direct classes and association. This is a good way to begin analysis, but it does not always supports. Sometimes we must raise the level of abstraction to solve a problem. We should be doing this throughout as you build a model, but we put an explicit step to make sure that you do not overlook abstractions. Last one is grouping classes into packages. This step of class modeling is to group classes into packages. A package is a group of elements such as association classes and packages with a common theme. Packages organize a model for convenience in drawing, printing, and viewing, etc. When we place a class and association in a package, we are making a semantic statement. Generally speaking, classes in the same package are most closer related than classes in different packages. For example, in a ATM machine, the packages might be a cashier station or ATM, and accounts. In that accounts, we have a card, customer, accountant, transaction update, etc. And also banks. Uh, these are all the steps we have to consider to build a domain class model. Next one is the domain state model. Some domain objects pass through qualitatively distinct states during their lifetime. There may be different constraints on attribute values, different association or multiplicity in the various states, different operations that may be invoked, different behavior of operations, and so on. It is often useful to construct a state diagram of such a domain class. The state diagram describes the various states, and the objects can assume the properties and constraints of the objects in various states and the events that take an object from one state to another. Most domain class do not require state diagrams and can adequately described by a list of operations. We must consider the following steps to construct a domain state model. Identify domain class with states, find events, build state diagrams, evaluate state diagrams. Here, when we construct a domain state model, first thing is to identify classes along with the state. First, examine the list of domain classes for those that have a distinct life cycle. Look for classes that can be characterized by a progressive history or behavior of cyclic behavior. Identify the significant states in the life cycle of an object. For example, a scientific paper for a journal goes from being written to under consideration to accept or rejected. There can be some cycles like that. For example, account in ATM machine, account is an important business concept, and the appropriate behavior for an ATM depends on the state of an account. The life cycle for account is a mix of progressive and cycling to and from problem statements. No other ATM classes have a significant domain state. Next one is finding states. List the states for each classes and characterize the objects in each class, that is the attribute values that an object may have, the association that it may participate in their multiplicity, attributes and association that are meaningfully only in certain states, and so on. For example, in an account, normally in normal cases, when the ATM machine is accessible, the customer comes for an ATM machine and draws the amount and logs out. And when the ATM is closed, the customer but still wait for the records of the bank. And when overdrawn, the customer withdraws and exceed the balance in the amount, and he suspend or access the account blocked for some reasons. Next one is finding events. Once you have a set of states, finding events that cause transition among states. Think about the cause a state to change. In many cases, you can regard an event as completing an activity. For example, in an ATM machine, important events to be included as closing an account, withdraw excess funds, repeated incorrect PIN, or suspected fraud and administrative action. These are all the events we have to suspect when finding the events. We can also find events by thinking about taking the object into a specific state. Next one is building state diagrams. The state to which each application add transition to show the change in the state caused by the occurrence of an event when an object is in a particular state. If an event is terminated from a state, it will usually have a single transition from that state to another state. If an event initiates a target state, then consider where it can occur and add transitions from those states to the target state. It is usually not important to consider effects when building the state diagram for a domain class. If the objects in the class perform activities and transitions, um, add them to the state diagram whenever it is needed. Last one is evaluating the state diagrams. Examine each state model. All the states are connected to each other. Pay particular attentions to paths through it. If it represents progressive class, then there is a path from the initial state to the final state. Are they expect variations present? If it represents a cyclic class, the loop is present. There are there any dead states that determine the cycle we are going to consider? Next one is a domain interaction model. During domain analysis, the emphasis is on key concepts and deep structural relationships and not the user's view of them. The interaction model, however, is an important aspect of application model. These are all about domain analysis. The next one is application analysis. In application analysis, the first model is an application interaction model. To begin with the interaction model by determining the overall boundary of the system, then identify use cases and bring out the scenarios and sequence diagrams and activity diagrams, and finally check against the domain classes model to ensure that there are no inconsistencies. We must consider the following steps to construct an application interaction model. Determine the system boundary, find actors, find use cases, find initial and final events, prepare normal scenarios, add variation and exception scenarios, find external events, prepare activity diagrams for complex use cases, organize actors and use cases, check against the domain class model. The first one to construct an application interaction model is to determine the system boundary. We must know the precise scope of an application, the boundary of the system, in order to specify the functionality. This means that we must decide what the system includes and more important, and what are all the necessary measures. If the system boundary is drawn correctly, you can treat the system as interaction with the outside world. During analysis, we decide the purpose of the system and the view that it represents to its actors. During design, you can change the internal implementation of the system as long as you maintain the external behavior. Next one is to find actors. Once you determine the system boundary, we must identify the external objects that interact directly with the systems. These are its actors. Actors include humans, external devices, and other software systems. The important thing about actors is that they are not under control of the application, and we must consider them to be unpredictable. That is, even though there may be any expected sequence of behavior by the actors. An application design should be so that it does not crash if an actor fails to behave expected. Next one is finding use cases. For each actor, the fundamental different ways in which the actor uses the system. Each of these ways in a use case, the use case partition the functionality of a system into a small number of discrete units, and all system behavior must fall under this some use case. Each use case should represent a kind of service that the system provides, something that provides a value to the actor. Try to keep all of the use cases at a similar level of detail. Um, for example, when we are drawing an ATM machine, ATM supply machine, when one person is going to apply loan for in the bank, and another use case should not withdraw the cash or amount from the savings account in the ATM. This finally shows how use cases should be. Next one is finding initial and finding final events. Use cases partition system functionality into discrete two pieces and show the actors that are involved with each other, but they do not show the behavior clearly. To understand behavior, we must understand the execution sequences that cover each use case. We can start by finding the events that initiate each use case, determine which actor initiates the use case, and define the event that is sent to the system. In many cases, the initial event is a request for the service that the use case provides. In other cases, the initial event is an occurrence that triggers a chain of activity. Next one is preparing normal scenarios. For each use case, prepare one or more typical dialogues to get a feel for expected system behavior. These scenarios illustrate the major interactions, external display formats, and information exchanges. A scenario is a sequence of events among a set of interacting objects. This will help to ensure that important steps are overlooked and that our overall flow of interaction model. Next one is add variations and exception scenarios. After we have prepared typical scenarios, consider special cases such as input maximum and minimum values and repeated values. Then consider error cases, including invalid values and failures to respond. For many interactive applications, error handling is the most difficult part of development. Finally, consider various other kinds of interactions that can be overlaid on basic interactions such as help request and status queries. Next one is to find external events. To examine the scenarios to find all external events, include all input, interrupt, decision, and interaction to or from users or external devices. An event can trigger effects for a target object. Internal computation steps are not events except for computations that interact with the external world. Use scenarios to find normal events, but don't forget unusual events and error conditions. Next one is to prepare activity diagrams from complex use cases. Sequence diagram capture the dialogue and interplay between actors, but they do not clearly show alternatives and decision. For example, we need one sequence diagram for the main flow of interaction and additional sequence diagram for each error and decision point. Activity diagrams let you consolidate all this behavior by documenting forks and merges in the control flow. It is certainly appropriate to use activity diagrams to document business logic during analysis, but do not use them as an excuse to begin implementation. Next one is organizing actors and use cases. The next step is to organize use cases with relationship. This include extend and generalization. This is especially helpful for large and complex systems as with the classes and state models. We define organization until the base use cases are in place. Otherwise, there is too much of risk of distorting the structure to match some concified notions. Similarly, we can also organize actors with generalizations. The last one is to check against the domain class model. At this point, the application and domain models should be mostly consistent. The actors, use cases, and scenarios are all based on classes and concepts from the domain model. The one of the steps is constructing the domain class model is to test access paths. In testing as an attempt to the use case. Cross-check the applications and domain models to ensure that there are no inconsistencies. Examine the scenarios and make sure that the domain model has all the necessary data. Also make sure that the domain model covers all the event parameters. Next one is application class model. Application classes define the application itself rather than the real world objects that the application acts on. Most application classes are computer oriented and define the way that users perceive the application. We must consider the following steps to construct a application state model, class model. Specify user interfaces, define boundaries of the classes, determine controllers, check against the interaction model. First one is to specify user interfaces. Most interactions can be separated into two parts: application logic and the user interface. A user interface is an object or group of objects that provides the user of a system with a way to access its domain objects, commands, and application options. During analysis, the emphasis is on the information flow and control rather than presentation format. The same program logic can accept input from command lines, files, mouse button, etc. During analysis, treat the user interface at a coarse level of detail and instead try to determine the commands that the user can perform. A command is a large scale request for a service. Next one is defining boundary classes. The system must be able to operate with and accept information from external sources, but it should not have its internal structure dictated by them. It is often helpful to define boundary classes to isolate the inside of a system from the external world. A boundary class is a class that provides a staging area for communication between a system and an external source. A boundary class understands the format of one or more external sources and it converts information from transmission to and from the internal system. The last one is to check against the interaction model. As we build an application class model, go over the use cases and think about how they would work. For example, if a user sends a command to the application, the parameters of command must come from some user interface object. The requesting of the command itself must come from some controller object. When the domain and application class model are in place, we should be able to simulate a use case with the classes. The next one is application state model. Application state model focuses on application classes and the domain state model. Application classes are more likely to have important temporal behavior than domain classes. We must consider following steps to construct an application class model. Determine application classes with states, finding events, build state diagrams, check against the class model, check against other state diagrams, check against the interaction model. These are all the steps to be considered when building an application state model. Thank you for watching this video. Thank you.